Hello students, this is lecture number 27. The title of this lecture is Dynamic Programming. It comes under special types of LPPs. Now the dynamic programming, as the name indicates, it means that it is dynamic as compared to a static programming problem. It means that it changes with respect to some factor, let us say with respect to time or some other factor. It is also called a recursive programming problem. The dynamic programming problem is based on the Bellman's principle of optimality, which was given in the year 1957. Now this dynamic programming method, it breaks down the decision problem into smaller sub problems, and these sub problems are solved so as to give the solution of the original problem. Now Richard Bellman's principle of optimality is as follows: an optimal policy has the property that whatever the initial state and the initial decisions are, the remaining decisions must constitute an optimal policy with regard to the state resulting from the first decision. Now let us take some examples to understand what exactly does this mean. So first of all, let us look at this simple problem, which is the case of a single additive constraint and additive separable returns. Now this means that suppose UIs have to be determined in such a way that UIs are the decision variables which minimizes the function f1 u1 plus f2 u2 like this up to fn un. Now this is a separable function, which means that the function can be written as a sum of different independent variables. For example, f1 u1 is a function f1 and it is only in the variable u1. Similarly, f2 is a function which is only in the variable u2 and like this. So these kind of functions are called separable functions. Now this is subject to just one single constraint of the type a1 u1 plus a2 u2 plus an un greater than or equal to b. Here all the ai's and all the b's, I mean there is only one b, they are all real numbers and they are greater than or equal to 0. ai's are greater than or equal to 0 and b should be strictly positive. Also the decision parameters use, that is uj, that is uj greater than or equal to 0, from j goes from 1 to n. So the decision variables, as you know, in a linear programming problem, usually the decision parameters are supposed to be greater than or equal to 0. Now the objective or the return function z is a separable additive function of n variables uj's, that is fj uj is a function of uj only, just as I have explained, and this is a n stage problem. Because why is it n? Because the number of decision variables are n and the suffix g indicates the stage. Now the ui's or the uj's are the decision variables. With each decision uj is associated a return function fj uj, which is the return at the jth stage. So in other words, the given problem has been converted into a multi-stage problem like this. So let us introduce new variables x1, x2, xn, which we will call as the state variables like this. First of all, we will define xn, which is equal to a1 u1 plus a2 u2 plus an un, and according to the given problem, this quantity should be greater than or equal to b. Then we will define xn minus 1 as a1 u1 plus a2 u2 plus a n minus 1 u n minus 1, which is greater than or equal to x n minus a n u n. This x n we have taken from the first equation. And like this we will go backwards, and finally we will define x 1 to be a 1 u 1, which is equal to x 2 minus a 2 u 2. Now this is called the backward recursion, because we have started by defining from x n onwards. So if on the other hand you define starting from x 1, then it is called as a forward recursion, but since we have just started with x n, so that is the reason why it is called as a backward recursion. Now after this we will also state the transformation functions, which are defined like this, that is x j minus 1 is equal to t j x j u j, where j goes from 1 to n, and this means that the each state variable is a function of the next state and the decision variables. So these are called the state transformation functions. Now since x n is a function of all the decision variables, we may denote by capital F n x n the minimum value of the function z for any feasible value of x n, and we can write f n x n as minimum over u 1 u 2 u n of f 1 u 1 plus f 2 u 2 plus f n u n, and the minimization has to be done over the non-negative values of u j subject to a x n, subject to x n greater than or equal to b. So in other words, we have defined the state transformation variables, we have defined the state variables and the state transformation functions. Now we will select a particular value of u n, and holding this u n fixed, we will minimize the z, which is the objective function, over the remaining variables, and this minimum will be given by f n u n plus f minimum over u 1 u 2 u n minus 1, f 1 u 1 plus f 2 u 2 plus f n minus 1 u n minus 1, which is actually equal to f n u n plus capital F n minus 1 x n minus 1. And the values of u 1 u 2 u n minus 1, which would make this function f 1 u 1 plus f 2 u 2 plus f n minus 1 u n minus 1 minimum for a fixed u n. So this depends upon x n minus 1, which in fact also in turn depends on the function x n and u n. So that indicates the recursive nature of the problem. Now also minimum of z over all u n for any variable for any feasible x n is f n x n, which is given by minimum over u n f n u n plus f n minus 1 x n minus 1, and if somehow f n minus 1 x n minus 1 was known for all u n, then the above minimization would involve a single variable u n, and like this, by repeating this argument we can get a recursive formula as follows: f j x j is equal to minimum over u j f j u j plus capital F j minus 1 x j minus 1, where j goes from 2 3 up to an n. Note that 1 is not to be written here, with the condition that f of 1 x 1 is equal to f 1 u 1 and x j minus 1 is equal to t j x j u j. This total concept of defining the state variables and the state transformation functions in a recursive fashion is called as a dynamic programming problem or a recursive programming problem. Now let us take a simple example to illustrate this procedure. Suppose we have the optimization problem u1 squared plus u2 squared plus un squared subject to u1 plus u2 plus u3 greater than or equal to 100, and the u2 and u3 are greater than or equal to 0. Of course, the u1 has also to be greater than or equal to 0. That is a typing mistake, sorry for that. So, we will define the decision variables which are the u1, u2, u3. We will define the state variables as x3 is equal to u1 plus u2 plus u3. This is the first decision state variables x3, and this condition is already given that it is greater than or equal to 100. So, we will write that x3 should be greater than or equal to 100. Similarly, going backwards, we will define x2 is equal to u1 plus u2, and this u1 plus u2 is actually equal to x3 minus u3, and finally, we will define x1 as u1 which is equal to x2 minus u2. So, that is the way the state variables are to be defined. Then comes the state transformation functions. We are defining them as follows: f3 x3 is equal to minimum over u3 and u3 squared plus f2 x2. This is the definition as I have explained previously, and similarly f2 x2 is equal to minimum over u2, u2 squared plus f1 x1, and finally f1 x1 is equal to u1 squared. This is possible, remember, because the in the problem that is given to us, note that each of these terms, each of these three terms are in one variable only, that is this first term is in u1, similarly the second term is in u2, the third term is in u3. So, each of the three terms are in different variables, and as per the definition this is called as a separable function. So, now once we have defined the state variables and the state transformation function, now let us proceed to find out what this f1 x1 is. And as you know that from this condition f1 x1 is equal to u1 squared, and now we will substitute the value of u1 which is equal to x2 minus u2, and the square has also to be taken. So, this means that f2 x2 is equal to minimum over u2, that is u2 squared plus x2 minus u2 squared, and now we need to minimize this this quantity which is given inside the bracket, that is minimize u2 squared plus x2 minus u2 whole squared, and in order to minimize it we will differentiate it with respect to u2, which will give us this condition 2 u2 minus 2 times x2 minus u2 is equal to 0, which gives us that u2 is equal to x2 by 2. So, here we have this condition u2 is equal to x2 by 2. Hence, capital F2 x2 is equal to x2 squared by 2. Similarly, what about f3 x3? f3 x3 is equal to minimum over u3, which is to be taken over u3 squared plus f2 x2, and we will now substitute this in place of this f2 x2, we will substitute x2 squared by 2 which we have just obtained, and we will get x2 in terms of x3 minus u3, because here we will substitute x2 is equal to x3 minus u3, and again for minimization we will have to take its derivative with respect to u3 and put it equal to 0. So, that gives us u3 is equal to x3 by 3. Hence, capital F3 x3 is equal to x3 squared by 3. Now, we know that x3 is greater than or equal to 100. This is the way that has been given in the problem. So, F3 x3 is the least for x3 exactly equal to 100. So, the minimum value of u1 squared plus u2 squared plus u3 squared is 100, sorry, this should be 100, and automatically by going backward you can see that u1 is equal to u2 is equal to u3 is equal to 100 by 3. So, that is the solution of this problem. Next, let us take another example which is slightly different in structure. This problem says that a student has to take an examination in 3 courses A, B and C, and he has 3 days available for study. He feels it would be best to devote a whole day to the study of the same course, so that he may study a course for 1 day, 2 days or 3 days, or not at all. His estimate of the grades he may get by the study are as follows. In this table we have the courses A, B, C and the study days, that is 0, 1, 2, 3. For example, if he studies study days are 2, then A 1 hour, B 3 hour and C 3 hours. So, how should he study so that he maximizes the sum of his grades? So, in this table the estimation of his grades is given, that is in the courses A, B and C he has, if he puts study days 0, 1, 2, 3, then his estimated grades are given by, if he studies 0, I mean if he does not study for any day, then in A subject he will get 0 grades, and in B he will get 1 grade, and in C he will get 0 grade. So, these are the grades, his estimated grades. So, the problem says that how should he study so that he maximizes the sum of his grades, that is the problem. So, how should he study so that he maximizes the sum of his grades, that is how many hours should he put in for each of the 3 subjects, or how many days he should put in for each of the 3 subjects, so that his overall grades are maximized. So, let us formulate this problem using the dynamic programming problem that we have learnt. So, let u1, u2, u3 be the number of days he decides to study the courses A, B and C respectively. So, let f1 u1, f2 u2, f3 u3 be the grades earned by such a study. So, with this definition the problem can be written as maximize f1 u1 plus f2 u2 plus f3 u3 subject to the condition u1 plus u2 plus u3 should be less than or equal to 3, and all the u1, u2 and u3 should be greater than or equal to 0 and integers. Now, the reason why I have chosen this problem is that number 1, this is a discrete problem because it is talking about integer variables, as you can see u1, u2, u3 should be integers, and secondly the constraint that has been given is of the less than or equal to type. So, with these 2 different characteristics, let us look at the solution of the problem. Now, the decision variables are uj's and the return functions are fj uj, where j goes from 1 to up to 3. So, the state variables can be defined as follows. X3 is equal to u1 plus u2 plus u3, which is less than or equal to 3. Similarly, x2 is equal to u1 plus u2, which can be written in terms of x3 as x3 minus u3. Similarly, x1 is equal to u1, which can be written in terms of x2 and u2 as x2 minus u2, and also we can define the state transformation functions xj minus 1 is equal to tj xj uj, where j goes to 2 3. Now, this recursive formulas are Fj xj is equal to maximum over uj, Fj uj plus Fj minus 1 xj minus 1, j goes from 2 and 3, and for F1 it is F1 x1 is equal to F1 u1, where F3 x3 is equal to maximum over u1 u2 u3, that is F1 u1 plus F2 u2 plus F3 u3 for any feasible x3. The required solution will be maximum over uj F3 x3. This is using the way in which we have defined the state variables and the state transformation functions. Now, the stage returns can be written like this. On the top we have uj, that is 0, 1 and 2, 3, and on the left hand column we have j, which goes from 1 to up to 3, and the state returns can be written as follows: 0, 1, 1, 3, 1, 1, 3, 4, 0, 1, 3, 3. This is based upon the stage returns as given in the problem. Also, we can define the state transformations as xj minus 1, where j goes from 2 to 3 like this. In the top we have uj, that is 0, 1, 2, 3, and on the left hand side in the first column we have the values of xj as 0, 1, 2, 3, and their corresponding entries are shown in the table. Please note that the entries over here, for example, this they are not defined. So, that is the reason why they have been shown with the dashed sign. Now, coming to the recursive operations, let us try to understand this table, how it is written. In the first column we have the x2 values, that is 0, 1, 2, 3, and in the top rows we have F2 u2. So, F2 u2 will depend upon the value of u2, that is u2 is 0, 1, 2, 3, and at the second part of the table we have capital F1 x1, and finally in the third part we have F2 u2 plus F1 x1, and the last column is the F2 x2. So, we from this table we have to obtain the values of F2 x2. Now, this is depending upon the way in which F2 u2, small F2 u2, this thing, and capital F1 x1 is defined, and this third is the sum. So, this is the sum of the two, right, and whatever you get, that is the F2 x2 is written. So, please note, for example, this 1 I have marked in red and this 1. So, 1 plus 1 is 2. So, therefore, this 2 comes over here, and like this all the entries can be verified. Then coming to the next stage, that is F3 u3, exactly in the same manner F3 u3 is written in the first part of the table. In the second part of the table we have written capital F2 x2, then in the third part is their sum, and finally F3 x3 is written in the last. So, here also you can just check these values, for example, this 3 and 2. So, 3 plus 2 is 5 and this 5 comes here. So, this 3 plus 2 is 5 which comes here, and that is the value of our F3 x3. So, the maximum value is 5. How is this maximum value? Look at these entries. So, the maximum value is 5, and if you trace the path backwards through the bold type numbers that are marked in red, we get the optimum policy as u3 is equal to 2, u2 is equal to 0, u1 is equal to 1. Just let us go back here and see, look at the tables over here. So, this tells us that this 5, from where did it come? It came from these red entries, and that is the reason why we get the value of our u3 as 2, u2 as 0, u1 as 1. So, this means that in other words for the best cumulative grade point, the student should study subject A for 1 day only, subject C for 2 days, and should not devote any time to the subject B. So, that is the way this discrete problem has been dealt with. Now, let us look at another situation where we have a single multiplicative constraint and a additive separable return. The problem is to minimize z given by f1 u1 plus f2 u2 plus fn un subject to u1 u2 un greater than or equal to k, where k is strictly greater than 0 and uj are greater than or equal to 0. Now, please note that this constraint is a multiplicative constraint, that is, it is a product of u1 u2 un, and for this reason we have to define the state variables in a slightly different fashion. So, the state variables xj can be defined like this: xn is equal to un minus 1 u2 u1 greater than or equal to k. Similarly, xn minus 1 is equal to xn by un, that is un minus 1 up to u2 u1, and finally x2 and x1 just as the way we have defined previously. Then we need to define the state transformation functions of the type xj minus 1 is equal to tj xj uj by denoting by fn xn the minimum value of the objective function for any feasible xn. We get the recursive formula fj xj is equal to minimum over uj fj uj plus fj minus 1 xj minus 1, j goes from 2 3 up to n, and f of 1 x1 is equal to f1 u1. So, exactly just as in the first example, the only difference here is that where we have the constraint is in terms of product instead of the sum. So, let us take an example to understand this. Let us take maximization of u1 squared plus u2 squared plus u3 squared subject to the product of u1 u2 u3 less than or equal to 6, where each of the variables u1 u2 u3 are positive integers. So, as before, the state variables are defined as x3 is equal to u1 u2 u3 which is less than or equal to 6, x2 is equal to x3 divided by u3 which is equal to u1 u2, and x1 is equal to x2 u2 which is equal to u1. Again, the state returns, that is fj uj, can be written as uj squared, where j goes from 1 to up to 3, and this is the data that is given 1 2 3 4 5 6. So, it is their squares. Remember, fj uj is uj squared. So, the square of 1 is 1, square of 2 is 4, square of 3 is 9, and like this. Then comes the state transformation functions, that is the xj minus 1, where j goes from 2 to 3. Here again in the table uj is represented at the top row, that is 1 2 3 4 5 6, and xj are shown in the column, in the first column, and the corresponding values that are shown here that in the table, and those which are not defined, they are shown with the help of a dashed line. So, the recursive operations are shown here, the x1 and f1 x1 for 1 2 3 4 5 6, this is given in the problem, and the table, this table illustrates the value of f2 u2 and the value of f1 x1 and f2 x2. So, here we find you can just verify these values that are shown in the table entries, and those which are not defined are shown with the help of the dashed line. In the second table we have the f3 u3 and the corresponding f2 u2 and the f2 x2. So, the maximum value of u1 squared plus u2 squared plus u3 squared is 38, which is given by the values u3 is equal to 1, u2 is equal to 1 and u1 is equal to 6. And from where this 38 come from? So, this is the 38. So, let us look at by tracing back. So, this is the place from where they have come. So, they are shown in the red entries over here, moving backwards, and they are corresponding to these red entries, and therefore, we can say that u3 is equal to 1, u2 is equal to 1 and u1 is equal to 6. So, these are traced back from the, that is why it is called as a backward recursion, and therefore, we can say that the solution is obtained as u3 is equal to 1, u2 is equal to 1 and u3 is equal to 6. The alternate solution, that is u3 is equal to 6 and u1 and u2 is equal to 1 and u3 is equal to 1, u2 is equal to 6, u1 is equal to 1 are also possible. First of these is shown in the tables that I have marked with the red entry. So, in this way we can solve this problem using dynamic programming. So, with this we come to an end of this lecture on dynamic programming, where we have studied the principle of optimality and we have seen some examples how we can use them to solve the dynamic programming problem. Thank you.